All right, so polyprotic acids. Remember, the whole thing with polyprotic acids is they have multiple protons. That's their whole deal. And those protons come off one at a time. So unlike something like calcium hydroxide, where both hydroxides leave at the same time, we don't have to think about one leaving and then another leaving. With our polyprotic acids, the first one leaves, and now that's in solution. It's floating around. And when a second proton tries to leave, there are already hydrogens, H3O plus, protons, whatever you want to call them, in solution, and Le Chatelier's principle says that that will shift the reaction which way? To the left. Flavor? So, oh, here's grape. I did this with my Chem 20 last night, and somebody wanted cherry, and I pulled out like 5 handfuls. There was not a single cherry. So they must be at the bottom, I hope. Right, so if there are already hydrogens in solution, that's going to shift this equilibrium to the left, which means that I'll get even less of this SO3 minus dissociating into H plus, on top of the fact that it already has a really small K value. And this is the guiding thing when you're thinking about ice tables, calculating equilibrium concentrations for polyprotic acids. The fact that my first ionization suppresses the second ionization means that the second ionization practically doesn't matter. Yes. To use the scientific term, yeah. Yeah, like if you really needed SO3 2 minus, sulfurous. Yeah, sulfurous acid. Yeah, if you really wanted a lot of SO3 2 minus, I mean, there are easier ways, right? We could also just add SO3 2 minus directly. Now that equilibrium does mean that if I add this in, this is such a small K value that it'll mostly go this way. Only add that and add base. So we make the solution really basic. We decrease the H3O plus concentration. That'll also force SO3 2 minus concentrations to increase. And we'll do an example calculation of like, if we wanted to know, not doing any of these other things to manipulate, how much SO3 2 minus there would be in solution.
So add a lot of like sodium hydroxide.
Yeah. Yeah. Just neutralizing it, you get a lot. There's K values. So again, first K value is usually much larger and also has a suppressing effect on every other K value. So if it's triprotic, it'll suppress those even more. Sulfuric acid is kind of the only exception to this because its first K is strong. It's a strong acid, so its first K is like a bajillion. It's all products, yeah. Then the second one is not particularly weak, but it is weak, technically. All right, so if we want to find the pH of this carbonic acid solution, we're going to do an ice table. And I'm going to write out a chemical reaction for this. What is my H2CO3 going to react with? Water. I always just kind of write it in there first, and this is one of those examples of doing the problem ahead of time. You might get stuck there because you're like, wait, I've only ever seen Dr. K just write it in. What actually do I put here? It's easy to copy. So you got H3O plus HCO3 minus. Liquid. And we've got a concentration for this first one, so that's going to be my initial. Change, equilibrium. We don't worry about H2O. Why don't we worry about H2O? Because we don't include liquids and solids. Exactly. So we don't include liquids and solids. So we're not including it in this. Concentrations of H3O plus and HCO3 minus initially is going to be 0. And then these change. Minus x plus x plus x. And this is something that I saw on the test. What the heck? This is like the priming line from a 3D printer. One of the things I saw in the test, there were a few people who had the sort of equilibrium expression backwards. It's not written the same every time. It just happens to be that a lot of the time we write it the same way, right? But it's always going to be products over reactants. And we always raise these equilibrium concentrations because the equilibrium expression, they always get raised to the power of their coefficient. Now in all of our acid-base problems, they're pretty much going to be, that coefficient is 1. So the exponent is 1. So we don't have to write anything in. Oh, and why am I not writing x? Or why am I not writing the minus x? Yeah, that was a bunch of people. Have grape. Oh, wait, that's not grape. The other one's grape. Who else? No? Okay, you can come get them later. If you want it. So x is, or k is really small. So x is going to be really small. So I don't need to worry about that x. So this is going to be equal to 4.3 times 10 to the negative 7. It's another one of those things that we do so, or I guess I do lots of examples in class. If you haven't done enough examples at home, then you might forget which number goes there or that a number does go there. Yeah, calculator time. So 4.3 times 10 to the negative 7 times 0.05. And then the square root. So x equals 0.000146629. So that's 1.2 sig figs. 1.5 times 10 to the negative 4. 1.5 times 10 to the negative 4. Those are the concentrations. But I need not just the concentration, but the pH. How do you calculate pH? Negative log. Do you want another Jelly Rancher? Okay. What you do is then you get a bunch of them, then you can pass them out to other people. You can decide. So negative log of the H3O plus concentration will give me the pH. .82.
And that would be proper sig fix.
And that would be proper sig figs. I was going to ask that next. On top of it. Because remember, sig figs for logs are weird. When you take the log of something, only the decimals count as sig figs. So to do 10 raised to the negative 3.82, that number that I got from that would have 2 sig figs. It would be pretty close to 1.5 times 10 to the negative 4. But we rounded, so. Now, oh, right, because this actually goes quick. So I kind of said, like, we ignore the fact that there's a second hydrogen that needs to be removed here. But I do want to show you in the math sort of why. I need another page. So now my second reaction for Ka2 is going to be HCO3 minus, and it's a Ka. So it's reacting with water. It's reacting as an acid, plus H2O. It's going to give me another H3O plus CO3 2 minus. So this is a second ice table in the same solution, which means that anything that I made in my first solution is also in my second solution. So what's the concentration of HCO3 minus? Wait, what did you say?
The HCO3 minus.
Yeah.
Be 0.050 minus the X.
Oh, that would be the leftover concentration of H2CO3 minus. Yeah. Right, so this is H3 or H2CO3. This is the carbonic acid. So yeah, if I subtract that, again, it is going to be a negligible amount. Won't affect it for sig figs. But we're looking for the concentration of HCO3 minus, which is over here. So there's really not very much in solution to begin with. Oh, don't want to use rounded numbers. 1.46629 times 10 to the negative 4. We ignore water. What else is in my solution? H3O plus. How much? The exact same amount. And this is actually fantastic. You'll see in a second why. And then if we wanted to find CO3 2 minus, you find CO3 2 minus. And again, because I've got this H3O plus already in solution, that is going to suppress this even more. On top of the fact that my K value was like something like 10 to the negative 8, 11, even smaller. So if we do the ice table here, this will be minus X. This will be plus X. Oh, sorry, this isn't X, this is 0. Got a little bit ahead of myself. It will be X. This is 1.46629 times 10 to the negative 4 plus X. This is 1.46629 times 10 to the minus 4 minus X. Somebody new. Why is this minus X? I did vibe code another app for drawing names. I don't want to use it.
I have a question.
Oh, yeah.
Did you say that H3O plus is going to suppress the HCO3 minus?
Just because of Le Chatelier's principle. So initially they're the same value. But because I already have something on this side, when the equilibrium shifts to the right a little bit, which it shifts to the right because this is 0, there's already something here. So it's not going to shift as much as if these were both 0. So that's like the suppressing effect. There's already something there, so I'm adding to a pile that's already got stuff in it. So I'm not going to add as much to that side. And if you wanted to see how much it is actually suppressed, you could redo this calculation, just make this 0. Assume that you're starting with, which would essentially be sodium carbonate, sodium bicarbonate, and see how much actually gets produced. We're going to keep it in here for now because it actually simplifies things. So yeah, this is going to shift to the right because I have a 0 for carbonate. Can't shift to the left. Even though my K value is 10 to the negative 11. So 10 to the negative 11 means that I can assume that X is going to be very small, because 10 to the minus 4 compared to 10 to the minus 11, that's 10 to the minus 7 different. So we can assume that these are going to be really small, which means that my equilibrium expression is going to be 1.46629 times 10 to the negative 4 times X divided by 1.46629 times 10 to the negative 4. That equals 5.6 times 10 to the negative 11. How do I solve for X? They cancel out. The concentrations are the same. It just cancels out. So X is equal to 5.6 times 10 to the negative 11, which means that it's equal to Ka2. So for every polyprotic acid, if it's just the polyprotic acid added to solution, we could make things more complicated by like adding something else to this. But if I just have a polyprotic solution that's added, or polyprotic acid that's added to solution, all of my concentrations for my second ice table, meaning the second ionization of the acid, and the amount of acid, they're always going to be the same because they both come from the first acid. Actually, it's the same kind of simplifying that happens. Oh, we'll do diprotic acid next week. But it kind of happens with your Ka, Kb, right? Where you can calculate things because when you measure the pH and you've added acid to it, the pH and the amount of the conjugate base are going to be the same.
But it wouldn't work out like this for sulfuric acid.
Correct. And I think the next one's sulfuric acid. Yeah. Dilute sulfuric acid solutions don't work out quite as nicely. But even if there was a... Let me think about that. Oh, I guess if you have to calculate the Ka3 for like... it doesn't quite simplify as nicely for like phosphoric acid. But they still end up being so small.
1.6 times 10 negative 11 is so negligible that you don't have to add it to the
Oh, yeah.
24.
Yeah. So my first H3O plus was 0.000. Did I even get? Yeah, okay. 1. Right, I've got squares now. 1.46629. So this is from Ka1. From Ka2, the H3O plus is 0. Well, I'm adding this X, 0.000 4, 5, 6, 7, 8, 9, 10, 5, 6. That's the amount that we'd be adding. And so, huh?
this from
Changes it by
0.01. It's from 3.82 to 3.83.
this seems like it's changing it by too much.
That's what I added those, and then took the negative log of them added together.
Yeah, yeah.
I mean, it's like 0.26%.
So long.
0.26. No, it's not. All right, so with sulfuric acid, though, it's a little bit different. For sulfuric acid, if we want to find the pH, then we do need to consider the second proton, and mostly because it's a strong acid for its first ionization, for the first proton. H2SO4 plus water, H3O plus HSO4 minus. What's my concentration of H3O plus going to be?
0.0075.
It's a strong acid. It ionizes completely. We don't even need to do an ice table. This is just going to be well, if I write out the ice table, I don't need to do any calculations though, because this will completely ionize. So this will be 0. This will be 0.0075. This will be 0.0075. Strong acids ionize completely. Now for the second part though, now I'm looking at HSO4 minus plus H2O, H3O plus SO4 2 minus. So I have 0.0075 molar of HSO4 minus. But unlike most ice tables where we have a weak acid, because the second ionization is a weak acid, I also have H3O plus already present. Which will still have a suppressing effect on that amount of acid, which is why this only needs to be considered for a dilute solution of sulfuric acid. How do we know it's dilute? I mean, 0.0075 molar, it's really small. That is very dilute. And honestly, if we had time, I would do another calculation and show you, like, with a higher concentration of sulfuric acid, to show you that the second ionization doesn't actually matter. Because this is like adding a strong acid to a weak acid. Just like if I added HCl to acetic acid. It's just that the strong acid that's being added is also making its own weak acid. So this is negative X, this is plus X, this is plus X. I think this one actually does work out to, or 75 minus X, 0.0075 plus X, X. Now, do you think that we'll be able to use the small x approximation here? Based on our typical rules, no. But before, when we were looking at when can we use the small x approximation, most of the time, I didn't already have something in the products. And I will say this, I wasn't expecting so many people on the exam to just do the quadratic formula, because every problem had a shortcut in a way that you didn't have to do the quadratic formula. And I will say, if at all possible, I will install shortcuts into problems that will reward you if you know about it, because we talked about them in class. But there will also be a way to solve it the long way around. Honestly, on a problem like this, because it makes it so much simpler, right? If I assume small x approximation, when I write this out, it'll be like the previous problem we just did, where I have 0.0075 times x divided by 0.0075 equals 1.2 times 10 to the negative 2. So it's worth checking just because there's practically nothing to calculate. Although I think actually, this isn't going to work. Because now 1.2 divided by 0.0075 is going to be, yeah, 1.6. 1.6 is quite a bit too big. For some reason, I thought that worked on here. Huh? Oh, to check to see if the approximation is valid. It's 5%. It's way too big though, so our instincts were good. I must have been thinking of a different problem. We cannot ignore x, which means that this will be quadratic. Uh, 0.0075 x plus x squared .0075 times 1.2 e to the negative 2. And then that plus this is 0.00759. No, it's not. There we go. And let's just polysolve this. 1.0195, 0, negative. So x is going to be 0.00385. 376786. Oh yeah, that's That's very significant. So this, right, is 0.0038. This is 0.0075. It's like 50%. So H3O plus is going to be 0.01135. My SO4 2 minus will 0.00385. And then negative log is 2.41 is the pH. So if we hadn't done that, the pH would have been 2.12 instead of 2.41, which doesn't sound like too much, but that's like 3x or 30% more. Done log math is weird. Any questions? Okay.
The significant figures like after the decimal.
Because the K was 1.2. And our initial concentration, was also 0.0075. Yeah. Oh. Ouch. Did I do something wrong? I added 0.0075 to, well, I added x to 0.0075. I got 0.0113537. And then did the negative log of the wrong number. Mm-hmm. .94. And this one should be 2 sig figs. Oh.
The polymer lot way necessary because it's both polyprotic and a strong acid.
Yes. Sulfuric acid is the only polyprotic strong acid. So really, this is the only time that you have to do this whole thing is when you have sulfuric acid. Otherwise, the first ionization will be weak, and so the second ionization will be even weaker.
So the pH don't have 466.
No. Even the pH in the answer in the top right there is 3 sig figs. Because only after the decimal counts. First number is just the power. All the rest of the numbers are the actual number.
the 3, when you convert it back, you should get times 10 to the negative 3.
If it's 1 times 10 to the negative 3, then you would get times 10 to the negative 3. If it's like, so like 5 times 10 to the negative 3, you would get 5 times 10 to the negative 3, I think you would get like 4.5. Something like that. It's a little bit weird because the negative exponent is how small it is. But if you're,
Wait, no, when I've been converting it, I get like 1 more than what it is. Like if it's 3, I get like 10 to the negative
yeah, because if it's this, that's halfway to being a bigger number. So this would be like, this was 5 times 10 to the negative 4. It would be 3.5.
Yeah.
Did that work? Okay, 3.3. Logs are weird. It's not the time. Not the time or the place. We actually already did this. So again, sulfuric acid, kind of an exception to the rule, but it's only an exception to the rule because it's strong in its first ionization, weak in its second ionization. Every other polyprotic acid is weak for every step, which means that the first ionization isn't very much. The second ionization is even less and suppressed by the first. So really, sulfuric acid is kind of in a class of its own. So if we want to know the anions formed by a polyprotic acid, we just did this actually with the carbonic acid, which is actually what this next problem is. Oh, but it says acid in it. I mean, it ends up being the second step of this same problem. But instead of, so we did this whole calculation where because the first one was weak, the first one gives me H3O plus and my HCO3 minus or bicarbonate. Then I have the same concentration for bicarbonate and the same concentration for acid, plus a really small K value. What are that? 5.6 times 10 to the negative 11. So then when I go to do this calculation, I can assume that X is really small, which means that when I write out the equilibrium expression, those concentrations cancel each other out. And so for every other polyprotic acid, aside from sulfuric acid, the concentration of the anion after the second or third ionization will be the same as the K value. Because everything else cancels. So we already did this. Oh, and this is just showing again how the amount of H3O plus produced from the second step is insignificant, and so it won't actually have a noticeable effect on the pH. It will have some teeny tiny effect. I don't have enough time for this. So acid strength, this is one of those things that you like memorize all these things as strong acids or weak acids just because it's easier. This is like explaining that a little bit. So some things like binary acids. What was that sound? you hear that? This water bottle? Yep. Sorry. Nope, it's not. It's something else. All right, so binary acids, you're really distracted by small sounds. Binary, it's not a symptom. It is a symptom. So I don't know if you've ever thought about this. So things like hydrogen sulfide or sulfuric acid, or no, hydrosulfuric acid, I'll struggle with that, is an acid, but CH4 methane is not. Or something like hydrochloric acid is a strong acid, hydrofluoric acid is not. Why is that the case? Well, to be an acid, it has to donate a hydrogen. To donate that hydrogen, it has to be willing to give up that proton, or it has to be willing to or able to hold on to all of those electrons that it takes from hydrogen, right? Because it leaves its H+. It doesn't leave with its electrons. So to act as an acid, we have to donate that hydrogen. So bond polarity and bond strength affect how acidic something is. If there is a really strong bond between the hydrogen and the anion, then they will mostly stay together, and that'll be a weak acid. The bond strength between carbon and hydrogen is really pretty strong. And so it almost never, probably just say never, loses those hydrogens, never ionizes, does not act as an acid. You can do some extreme things to make it act like an acid, but those are very, very reactive. So then the bond strength between hydrogen and sulfur is a lot weaker, and so that hydrogen can leave. So for anything to be acidic, we must have a polar bond where the hydrogen is the positive pole. This is also representing how those electrons get distributed between the hydrogen and whatever the anion is. If I have a more electronegative element, then it will pull on more of those electrons and pull them away from the hydrogen. So this is why like metals don't act like acids, like HI, which would be called lithium hydride. The hydrogen in that case would actually leave with all of the electrons. So this hydrogen is more electronegative than lithium. Lithium wants to be a positive charge. So when this reacts, or if this hydrogen leaves, it actually takes the electrons with it. If they're essentially neutral, then those electrons are shared. It's not going to act like an acid. But in something like hydrofluoric acid, where fluoride has like the highest electronegativity of any element, it really has all of the electrons. Hydrogen has almost none. So just based on bond polarity, you might expect hydrofluoric acid to be a strong acid. But because the hydrogen and the fluorine are both, well, more specifically, the fluorine is so small, so we have to consider bond strength also. The closer two atoms can get to each other, the stronger the bond. Fluoride is really small. It's really holding on to all those electrons. But because they're so small and so close together, makes it a weak acid. So something like hydrochloric acid, actually, wait, cool. Hydrochloric acid, chlorine, is a much bigger atom than fluorine is. Also very electronegative, but that extra size means that the hydrogen's farther away, means they have a weaker bond. It's easier for the hydrogen to leave. On top of the fact that when it does leave, chlorine has more space for more electrons than fluorine does. So things that are electronegative and are also, I guess, really kind of second row and below, larger atoms, are the ones that tend to be strong acids.
So weaker bond makes a strong acid, stronger bond makes a weak acid.
Yes. And electronegativity also plays into that polarity. So like this chart here is right, increasing electronegativity increases the strength. So hydrofluoric acid, not a strong acid, but it is a stronger acid than water is. Increasing size also increases acidity or decreasing bond strength. So going from water, H2O, to hydrogen sulfide or a hydrosulfuric acid. Sulfur is a larger molecule, has a weaker bond with those hydrogens, easier for them to leave. It's a stronger acid, not a strong acid, but stronger acid than water. And so you keep going down, keeps getting stronger. So kind of two effects at play, very similar to electronegativity in general. In terms of size, as things get larger, they get less electronegative. But also as their effective nuclear charge increases, they become more electronegative. We got like a dual trend on the periodic table. Going down is less electronegative, going left is less electronegative. So then our oxyacids, oh wait, what time is it? Okay, we'll talk about oxyacids on Monday.